All right, hi guys. Welcome to my special honors lesson on piecewise functions. So you've probably been introduced to piecewise functions in the past, you just haven't spent a lot of time with them. All piecewise functions are piecing together different functions all in one graph, just depending on what x is. So an example of that would be like we did a quick example, or let me show you a quick reference to what we did in class. We were talking about two different salary plans, and one of them was linear, and then the other one was exponential, and eventually outgrew that linear rate of increase for the salary. So a good example of piecewise functions would be to talk about a salary that increased. Let's say you started at a company with a linear increasing salary, and then after a certain amount of years, maybe 10 years, you started increasing exponentially, maybe with a percent raise rather than a constant raise. So at that point, you might be at a linear raise every year and then switch to an exponential every year. So this, from everything less than this x value would be a linear function. Everything after it would be an exponential function. So piecewise functions piece together different separate functions all on the same graph, and like depending on x. So if x is less than 1, so we'll just jump right into this first example. If x is less than 1, we'll use this linear function 2x plus 3. At 1, or sorry, negative 1, if x is less than negative 1. At 1, we jump to, and from negative 1 to positive 2, we jump to this new function, absolute value of x minus 5. And then that stops at 2. And then at 3, a new function starts. The function itself just equals 1 from beyond that. So to graph a piecewise function, you just graph each of the separate pieces one at a time. So as long as x is less than negative 1, we're going to have the function 2x plus 3. So you're used to graphing the y-intercept of 3 and a slope of 2. So we would put a point at 3 and then go up 2 over 1. And then left 2, down 1. However, this is only for when x is less than negative 1. So I'm not actually going to graph this part of the line right there. I'm actually going to graph it only for x values that are less than negative 1. So I'm not going to have the y-intercept in that other point. In fact, the farthest I'll go on this function is this point right here, where x is negative 1. And then I can continue for those x's lower than that. So down 2, left 1, down 2, left 1. So this piece of the function continues up to negative 1 when x is negative 1. But at negative 1, see how it is strictly, this is the function for when x is strictly less than negative 1. That means that at negative 1, I don't have a point, I have an open circle. So I've drawn the first piece of this piecewise function. Next, from negative 1, so here I'm at negative 1 when x is negative 1, I'm jumping to this new function because it's defined for when x is between negative 1 and 2, and it includes negative 1 right here. So that means I'm going to have a filled in circle on this function. All right, so the absolute value of x minus 5. So we have to apply what we have learned about absolute value functions. It's that function that looks like a V, but I'm going to shift it down 5. So it's got a vertex right here at 5. And then from there, I would go up and out, and then up to the left as well. But as far as this tells me to go, which is when x is negative 1. So I'm going to stop right there when x is negative 1. And this function will continue as long as x is strictly less than 2. So I'll continue since x is 2 right here. This function will continue to that point with an open circle because x is strictly less than 2. So let's start where we started was this linear function up to when x is negative 1. We jump to the absolute value function at negative 1, absolute value of x minus 5, all the way up to 2. And then at 2, this function ends. A new function begins for x is greater than or equal to 3. And that is just the horizontal line where y equals 1. But that doesn't occur until 3. And because it is a inclusive, meaning it includes 3 in that, I can fill that circle in, and the last piece of my graph will go infinitely that way to the right. So now let's talk about, now I know this probably seems confusing right now. I'm going to do 2 more examples with you. So by the time we're done with all of them, you'll probably feel a little bit better about piecing together a piecewise function. So now D subscript f, that just means what's the domain of f, what's the range of f, and then we'll evaluate the function at these 3 points. So the domain of this function is all of the x values I can plug in. So let's look at that visual right here. So I can plug this arrow right here, means it's going to continue forever. So all x values up to -1. But since the function is defined at -1, it just jumps down here. Even though it's not continuous, I do still have a defined function at 1. So all the way -infinity, all the way up to 1, including 1, moving past 1 is in my domain. Right here is where I see this gap between 2 and 3. There's no function to find there. So my domain would be -infinity all the way up to, but not including, +2. And then my function picks up again with the domain picking up at 3 to infinity. So I would put that union sign, 3 to infinity. Again, the domain are all of those x values represented in this function. The range is the output, the y value. So this arrow right here is telling us this is going to continue down infinitely. So we'll start at -infinity for the range. And then we go up. We see all of these values are included. This piece stops right here, but this piece of the function is still having output values all the way up to +1. It never gets higher than +1. So -infinity to 1, and we'll include 1 because it does actually equal 1 right there. So there's the complete graph of this piecewise function, and there's its domain and range. So now we'll evaluate the function f of 1. So depending on your x value, that's how you choose which function you're going to plug 1 into. So when x is 1, we figure out which one of these 3 subdomains that's included in. So since 1 falls between this subdomain, -1 to 2, 1 falls in that, that means I'm plugging it in to that function. So the absolute value of 1 minus 5, which is -4. Or we can look at this visually, evaluate this function when x equals 1. So I just go to my graph, x equals 1 right here. The value of the function right there is -4. So that's probably the easier way to do that, is just using the graph. So let's use the graph for f of 6. Go to your x value of 6. That's on this piece of the function where y always equals 1. So that's the value of the function there, 1. F of 0, I would evaluate, that's my absolute value piece, and the function equals -5 right there. All right, let's look at another one. So we're gonna look at number 2 together now. So we've got 3 pieces again, 3 of these, what I'm just calling subdomains. So if x is between -4 and -2, so let's think about what that means on the graph. I'm gonna use pencil here because I'll erase it eventually. Between -4 and -2. So I don't know if you guys can see me kind of like putting a little bar of the x values. That's not part of my graph. I'm just visualizing where this piece of the function is going to fall. -x. So -x, remember, that is a linear function. So this right here, think of it as y equals -x plus 0. So it's a y-intercept of 0 and a slope of -1. Typically, what we would do is draw that line right here, right? But it's a piecewise function, so that's the pattern only between -4 and -2, including -4, not including -2. So I will kind of piece that together by imagining where I would place my line right there. And I'm including -4, so I can put a filled in circle at -4 all the way up to -2 with an open circle. Okay, sorry, I had to pause for a sec. All right, so that's the first piece of my function. I'm going to erase my pencil mark. So I would always, obviously, I always recommend pencil with math problems, but especially on these piecewise functions, because you may have to draw the whole function and then erase it so that you just have that piece of it. Okay, the next one, between the values of -2 and 1. So from -2 to 1. So just that little piece of x is there. Then I have this other linear function, x minus 3. So that's a linear relationship with a y-intercept of -3 and a slope of +1. So a y-intercept of -3 and a slope of +1, but only on this little window of x's. All right, so at -2, that's included. So at -2, this is the piece of the line I would have. I'll make it darker. It would be right there. So now I'm going to go over with pen, just so you guys have a better visual. So at -2, I can include it, so I would have a closed circle. But at +1, that is not including 1, so I'll have an open circle there and then fill in the line between. So that's the second piece. So the function jumps from this piece, and then at -2, it jumps down here up to 1, and then at 1, I'll jump up to this new one, x squared minus 2. So now we're throwing in a quadratic. So this is going to be a parabola with a vertex at -2. So while it does have a vertex at -2, this function doesn't start until x equals 1. So while I would typically put my vertex right here at 2, I'm going to not put a point there, but visualize the vertex there and go over 1, up 1. And since now I'm at x equals 1, I can put a point there because that's where the function starts. Then back from my vertex, which would have been at 2, I can continue building only to the right though. So I would go over 2 and then up 4 and put another point right here. And then I would go from my vertex again at -2 over 3 and then up 9. 5, 6, 7, 8, 9. Okay, so I've got these 3 points on my parabola that will finish off. And this is the rest of this piecewise function, because anything greater than 1 is going to use that parabola equation. So these are my 3 pieces. So this piece of a line, this piece is of a line, and then it jumps up to that parabola. All right. Hopefully you guys are feeling all right with this so far. It's hard when I don't have your feedback. Okay. So let's talk about domain of this. This domain starts at -4 because that's the first thing we see on our leftmost piece of this. The smallest x value is -4. We include -4. So the domain would be bracket -4. We can plug in x values. We can plug in -2, even though it's not included here. It is down here. We can go all the way to here at 1. It jumps to a new function. We can plug anything greater than -4 in. So -4 to infinity. The range, while this arrow indicates it will continue up forever, the lowest it gets is this value down here of -5. So our range is -5 to infinity. So now we're at a point where we can evaluate some of these values, f of -4. So you would just go to -4 and figure out what piece of the function is there, and that y value is your answer there. So the function value at -4 is +4. The function value at -2, this one's a little tricky because -2 is where the function jumps from this first line to the second line. So the answer to f of -2 is coming from this middle equation, because that's the filled in circle. So it's an open circle here on this line, which means that's not the answer. It's where it's filled in. That's the actual function value. So -5. And then f of 1, same thing with f of 1. The answer to that is the filled in circle, the one that's including 1, which is coming from this last one of -1. Okay, so there's 2 examples of piecewise functions. This next one, circle that. I want you to complete that one on your own. It's very similar. We've got two pieces of this function. The only difference about this one is it's not really in order. It's almost like backwards. So here we're starting with the top, the farthest right piece of the domain when x is greater than 5, and it's kind of working backwards. You can just start at the bottom and graph them in the reverse order. It doesn't matter. You can graph them in any order you want. All right, but I do want to go over with the following, number 4. So I want to go over number 4 with you as well. And then the remaining problems, I'm going to ask you to complete for homework and then turn in on the due date that I specified to you. Okay, number 4. We've got two pieces only. One of them is linear and one of them is quadratic. Let's start with the linear one. That one's a little simpler. As long as x is less than -2, this function is linear with a slope of 1 and a y-intercept of 5. So a y-intercept of 5, 1, 2, 3, 4, 5. Now, I'm not going to actually put my point there because this is the function rule only when x is less than 2. So I'm just going to visualize, or you can lightly draw it in. The slope is 1, so we would typically go like that, right? And then down this way. But -2, and not including -2, so I'll have an open circle there. Use my pen. So that's where I'll have my open circle. And everything less than -2 has this, is using this first linear function. So that's my first piece. Erase what I had there. Okay, my second piece will pick up, again, still at -2, but I'm jumping to this quadratic at -2. And we'll start with the filled-in circle since it's greater than or equal to -2. However, this quadratic is not in graphing form. So that's why I wanted to do this one with you guys, because we need to rewrite it. So think of this, if I had said, find the vertex. We had two strategies for that because it's not in graphing form. But if we know the vertex, we can put it in graphing form. Let's do completing the square. I think that might be easier. So completing the square, let's review that. I'm going to jump down here. Completing the square with a problem like this. I always refer to it in terms of those algebra tiles to visualize. So I have a giant x squared tile. I'm going to use an area model for this. I have an x squared tile down in my bottom left corner, and I want to continue building a perfect square with these two x's. So if I have two x's and I want to continue building a perfect square, I have to split those two x's evenly on either side of this. So I'm going to have one of them here and one of them here, which means my dimensions of my perfect square, so that little piece is x by x, which means to multiply x by what to get x here is just going to be 1 and 1 there. So to complete the square, what I'm going to have to do is add 1. So 1 times 1 is 1. To complete the square, I need to add 1. Well, I already have 3. So we can think of it as y equals x squared plus 2x plus 1. That's going to complete my square. So this is my perfect square. That leaves 2 left right here from my original 3 that I had. So this that I put in parentheses is my perfect square. Instead of writing it as x squared plus 2x plus 1, I can now write it as x plus 1 times x plus 1, or x plus 1 squared, plus 2. So I know I went through that a little quickly, but I just wanted to review completing the square. So this is what I have here, which will begin at x equals -2. So let's think about this. So my h and k, x plus 1 squared means my h value, this has a vertex at -1, +2. So -1, 2. So -1, 2 is where my vertex would be, okay? And wait a second. From there, I would go up 1, left 1, up 1. And from that vertex, or right 1, up 1, left 1, up 1. So I land right back on this open circle. And that's where that's okay, because my parabola is going to actually go right on top of that open circle, which is fine. It'll just mean it's a smooth transition from one function to the next. Then I would go over 2 up 4 in both directions. There we go. Oops, no, I wouldn't go that one. Not that one right there, because then I'm already on that linear piece of it. Okay. So from there, this parabola would continue only in that direction to the right. And if it seems if you seem unsure of this value here at -2, you would just plug it in and make sure both of those have an output of +3. So -2 here is 3. -2 plugged in here would be 4 minus 4 plus 3, which is also 3. So these both have the same output for -2, which means it doesn't really jump to the next. It doesn't jump anywhere. It just starts where it left off and then continues. All right. So now let's evaluate this function at these different x values. F of 3. So the f of 3 is not on my graph. It's too high. But since 3 is greater than -2, I would plug that into this second piece. So it would be 3 squared, so 9, plus 2 times 3, which is 6, plus 3. So that would have a y value of 18. So that just goes off my graph. But we can still evaluate it with the equation. F of -4, that one I can just rely directly on my graph. -4, 1, 2, 3, 4, that would have an output of 1. And f of -2, we already saw that. It's the same for both pieces, and we see that in the graph here as well, has an output of +3. Okay, so hopefully you guys are feeling pretty okay about piecewise functions. The remaining problems on this, which would be that first one on the front, and so that first one on the front right here, number 3. We did 4, I would like you to do number 5. So 3, 5, 6, and 7. Those 4 problems I would like you to complete on your own and turn this in on the due date that I told you. And that's it. I'll see you next time. Feel free to stop in if you have any questions on this, because I know it is pretty new content. I'm happy to go over any questions you have. I will see you soon. Bye, guys.